Another electrophilic aromatic substitution is called nitration. And nitration is when you take nitric acid and concentrated sulfuric acid, and that's going to attach a NO2 group to the benzene ring, and that is called a nitro group, hence nitration. And in order to do this, we're following the same general electrophilic aromatic substitutions. We need to generate a strong electrophile. And that's what the sulfuric acid is going to help accomplish here, is we're going to take our nitric acid right here, which looks like this. So we have a nitrogen, double bonded O, OH, like so. Okay, like that. Okay. And that nitrogen has 4 bonds, so that has to be positively charged. We have a lone pair there. Okay. Now we're going to have our sulfuric acid present. What does sulfuric acid look like? And like that. Okay. So the first step here in this mechanism here is that we are going to do a proton transfer. That's a little bit different than all the previous mechanisms that we've been looking at. And so we'll write it right here. We have a proton transfer. And we can see here that what we need to have happen is that we need 1 nitrogen and 2 oxygens. When we look at nitric acid, we have 3 oxygens. And so we have to find a way to get rid of one of these oxygen groups here. And so we're going to protonate this oxygen right here. Okay, like that. Now, maybe worried like, why are we not using this negatively charged oxygen? And the reason why we're not using the negatively charged oxygen in this particular case is because this negative charge or these lone pairs are caught up in resonance with these 3 atoms right here. And so we're going to use this lone pair right here to protonate that. And what's that going to do is it's going to convert it into a good leaving group. Because like I just talked about, we need to get rid of one of those oxygen atoms. Right there. Okay. And what do you see right there? We have 2 positive charges right next to each other. That's not very good, right? And what else do we have? We have this species right here, still left over, the conjugate base of the sulfuric acid. So we have that. So we have that species right there. Okay. So we have a proton transfer. Now we have this species that is highly charged. Okay. Now what's going to happen here is a heterolysis step. Like that. And this one's interesting because now, look, we have this negative charge and it's going to do resonance. Or, that's not the right way of saying it. We can take one of these lone pairs and bring it down, and when that brings that down, this guy has to kick it off. Or we would break the octet with respect to that nitrogen atom right there. So this would be our heterolysis step. And that's going to give us this species right here, an oxygen, double bonded to nitrogen, double bonded to oxygen, plus water has fallen off right there. Okay. But that is still going to be positively charged right there because that's a nitrogen atom with 4 bonds. But the way I've drawn it, Mercer theory doesn't say it's going to be like that. It's going to be a linear molecule looking like that. And that species right there is called the nitronium. A nitronium ion. Which is a really good electrophile. So we will do a electrophilic addition step. And that is when you are going to take your benzene ring. There's our benzene ring. Pi electrons attack the electrophile. And we're going to have to bring some electrons over there, or we would form a Texas or a nitrogen that would break its octet. So now we have this species. And so you could draw it like this if you wanted. Like that. Okay. But then that nitrogen still has 4 bonds, so it's positively charged. We have a hydrogen there. We still have our hydrogen there. That's lacking an octet, so that carbon has to be positively charged. And so our next step is going to be a electrophile elimination step. And how are we going to do that? Well, we need a base. And so what do we have around that can act as a base? We have water. We have a conjugate base of sulfuric acid. All would work. So let's take the water here and come and restore aromaticity to look like this. And the way we write it, we just go NO2 for the nitration. But the nitro group is a nitrogen doubly bonded to oxygen, singly bonded to an oxygen with a negative charge, and then the nitrogen itself is going to be positively charged. But what am I missing here? There. Has to be an aromatic compound. And so what else did we generate? We generated hydronium, which is analogous to sulfuric acid. That's a strong acid, that's a strong acid. It's pretty much saying the same thing. And so that right there is a nitration.